Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over bond lengths and how that relates to resonance structures. So let's get into this. So in this problem we're asked, or we're given, the average bond lengths for several carbon-oxygen bonds. And so we have the single bond here. So the single CO bond is 143 picometers. The double bond here between carbon and oxygen is 123 picometers, and the triple bond between carbon and oxygen is 109 picometers. And you'll notice that as you go from single to triple bonds, the length of the bond is decreasing. This makes sense because you're adding more electrons that are being shared between the atoms. The electrons are negative. The nuclei of the two atoms are positive. They're going to be more attractive or more strongly attracted to the electrons being shared. And so that's going to draw them closer together. Okay, so here we're asked in the ion, the CO3 2 minus ion, the carbonate ion, all three carbon-oxygen bonds have identical bond lengths of 136 picometers. Explain why. Okay, in order to answer this question, we first need to understand, we should draw the Lewis dot structure for the carbonate ion. And when you do that, you should get carbon with the three oxygens bonded. So we'll have the three oxygens, and one of them is going to have a double bond on the oxygen. So we'll have lone pairs there, three lone pairs there, and three lone pairs there. And we should have our brackets because this is an ion with a charge. So we'll have the 2 minus charge on the outside. So here is the Lewis structure for the carbonate ion. And the one thing you should notice right away is that this can undergo resonance because this double bond doesn't have to be between this oxygen and carbon, but it could be between this oxygen and carbon. We can move the electrons around. We can bring these electrons down and create a double bond, right? So let's go ahead and draw our other resonance structures. So then if we bring the electrons down and create a double bond here, then the electrons in this double bond will go onto this oxygen, right? So if I draw, I need here. So I can take these electrons, go that way, and then the electrons in one of in the bond here could go here. And so that's going to form a different resonance structure. Oops. So now we'll have the double bond here, and we'll have this single bond here with the 2 minus charge. And then, oops, I forgot my lone pairs here. And or what could happen is you could have the lone pairs here, right, could go there and then push these electrons or a pair of electrons here, and then we'll go back up onto the oxygen. And so we can draw our third resonance structure. So then we'll have the double bond between this carbon or this oxygen and carbon. Like so. And here we have our three resonance structures. And again, this can, this can go, and we can move the electrons and come back to this one. But I want to give you an idea of how we get those resonance structures. Now, here you'll notice this double bond could be here, it could be here, it could be here. I want to stress that this is not really what's going on with the molecule. This double bond is not moving around. We're not moving electrons. This double bond is not going from one carbon to the other. It's not fluctuating like that. That's not what's happening at all. This is just a way that we can kind of depict that. But we can do the best we can. But what's really going on here is that the double bond character is kind of shared evenly among all of the atoms. Oops, I messed up my arrow here. So you can think of the actual molecule, the actual ion, the polyatomic ion here, as being a hybrid of all three of these. And so this double bond character is divided evenly among all of the atoms, of all of the oxygens. So what it will look like if we were to draw it better, I guess, would be we would have the oxygen bonded to the carbons, or the oxygens bonded to the carbon, like so. And so then you'd have one complete bond, but then that double bond is shared evenly. So we're gonna have a hybrid bond such that each of these bonds are going to be equal, right? But they're not going to be single and they're not going to be double. They're going to be somewhere in between, right? If we determine the hybrid of these, then I can average these, and we'll get like an average bond. So the way we determine that, or the way we depict that, is by a dotted line. We'll have one full line and one dotted line, indicating that it's somewhere between a single and double bond. It's not a single bond, it's not a double bond, it's somewhere in between, and that's how we depict it. 2 minus, okay? And we can, put lone pairs on here, like so. Now, how do we determine what the bond length is going to be? Well, we have to figure out what the bond order is, and the bond order is another fancy word or fancy phrase for determining how many bonds we have between the atoms. And the way you do that is you take the number of bonds in your Lewis dot structure, right? So here I have 1, 2, and I have 3, 4 bonds, right? I have a double bond, I have single, single. So I have 1, 2, 3, 4 bonds, and then I divide that by the total electron groups. And the thing to remember is when we think about electron groups, single, double, and triple bonds are considered one group, right? So this single bond is considered one group. This single bond is considered one group. And double bond is not considered two groups, but one group. So I have a total of 1, 2, 3 electron groups, but I have 4 bonds. So I take the bonds, so here, I'll write down here. So bond order is equal to number of bonds divided by, I should say number of electron groups. Okay, so the bonds I have here again is 1, 2, 3, 4. So that's going to be equal to 4 for the number of bonds. divided by, and then I have 1, 2, 3 atoms, right? So each atom is bonded by electron group. So 1, 2, 3 atoms. And so that's going to be 3. So that's going to be 1 and 1/3 bonds. So each of these are equal, like I shown here. So this is going to be 1 and 1/3 bond. This is going to be 1 and 1/3 bond. This is going to be 1. I keep doing the same thing. 1 and 1/3 bonds. Okay, so now what do we do with that? Okay, well, look at the difference here. I have a single bond is 143 picometers. A double bond is 123 picometers. So I have 1 and 1/3 bond here. So I know it falls between 143 and 123. And they're telling me that it's 136, which falls between those. But can I do better? Yes, I can do better. So, what is the difference between 143 and 123? That's going to be the difference in the length of the bond. If I subtract 123 from 143, 143 minus 123 picometers is equal to 20. So that's the distance in length, or the difference in length, you can think of it as distance, between the single and double bond. That's going to be the 20 is the difference, right? Well, we can take 1/3 of 20, right? So if we take 20 and divide it by 3, we'll get 6 and 1/3, or 6 and 2/3. 6 and 2/3. 6 and 2/3, which is the same as 6.6 continued. Okay, so now, that would be the number of picometers for 1/3 of a bond, right? So notice again here, as you increase the bond order, right? As you increase the bond order from single to double to triple, the length of the bond decreases. So here, we're going to increase the bond order from 1 to 1/3 of a bond. So we're going to increase it towards the double bond by 1/3. So we're going to add 1/3 of the bond character. So if we're going to go towards the double bond character by 1/3, then that we're going to shorten the bond length by 1/3, right? So again, this is picometers. So this is the bond length that's related to 1/3 of a bond. So if we're going to increase the bond order from 1 to 1/3, then therefore we're going to decrease the length by 1/3. And so we're going to decrease the length here, 143, by 1/3. So we take 143 and we subtract 6.66, right? That's going to get 666. So that's going to be 6 continued. So that's going to be, let me write this out correctly. So 143 picometers minus 6.6 continued picometers. And that's going to give us 43 minus 6 is going to be 137, minus 0.6 is going to be 136.4. So 136.4 picometers is what we end up with for the estimation of the bond length, which fits with what we're given here, rounded to 3 sig figs. And that, ladies and gentlemen, is how you can explain why all of the bonds in your carbonate ion are equal in length and why they are 136 picometers. I hope this was helpful. If you got your mind blown by this, then by all means, like the video, share the video, hit that like button somewhere over here, somewhere. You can find it. Also, make sure that you subscribe to my channel. Do me a favor here. I'm working hard for you. Show me some love. Also, hit that notification bell when you do that. Make sure that you click all so you can be notified by all the videos that I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you need help with a problem or question, if you have a topic you would want me to cover, put that down below so that way I can do that for you. Thanks for joining me and have a great day.